All right, friends and neighbors, welcome back. We are doing CCNA Chapter 24, OSPF Neighbors and Route Selection. And it turns out that this is the video that we're going to use to close out the whole OSPF series. Now, if you've been watching through all of these, you're probably like, it's about time. But we're going to break some things today, so maybe that's a fun way to close things out. So in this video, as always, we'll do the key topics, some of the big ideas from the chapter. Our exam section is IP connectivity, determine how a router makes forwarding decisions. And what we're going to touch on there is we're going to add stuff outside of OSPF. So we're going to do, I'm going to say it a bunch of times, prefix length, admin distance, and then the metric. Those are the really big ideas. And then, of course, we're going to fool around with our OSPF configuration items. Most notably, we're going to break things that would stop us from being a neighbor. And then we'll finish up with the do I know this already questions. So the key topics from this chapter are the OSPF requirements for neighbors. We know that all nodes or all OSPF routers that are doing the same thing can become neighbors, but not all neighbors will have an adjacency. But all adjacencies will be neighbors. Now, it also turns out that just because you're an OSPF router and I'm an OSPF router doesn't necessarily mean that we're going to be neighbors. There's a lot of things that have to be the same. We'll go over some of the show commands again. We've come to know and love a bunch of OSPF show commands. We're also going to talk about, what would cause things to fail. That's the breaking thing that I was going to mention earlier. And then we'll go over the default Cisco administrative distance settings. Now, we've been talking about OSPF. OSPF has an administrative distance of 110. But of course, we are going to talk, we're going to add, because this is outside of OSPF or it's bigger than OSPF, we'll add some other administrative distance settings in there. And these are important for you to remember for not only the test, but also just working with routers in general. There'll be a comparison between EIGRP and OSPF in terms of administrative distance. We'll look at what happens if a router has multiple pathways to the same destination, and what happens if they look kind of the same, but they're not really. And then we'll talk about overlapping routes. Now, in this case, really what overlapping routes is different subnet mask lengths. And then we'll go over some of the things that we see in a routing table. Okay. So what will allow OSPF routers to become neighbors? We know that we discover neighbors via the hello message, right? We're blasting that out. And the minute two routers find each other, then they're going to determine whether or not they can actually be neighbors, whether they can go to that two-way state. They have to be compatible in terms of their settings for that to happen. And so there's a bunch of stuff that has to happen before they can become neighbors. So the sort of stages that we go through is that they can find each other. And at that point, they can find out whether or not it's okay to be neighbors. And if they're neighbors, they might become adjacent. But there's nothing at all that says they're going to be adjacent and nothing at all that says that they're going to be neighbors. So there are some requirements to be neighbors. Obviously, the interfaces have to be up, right? That makes sense. And we're not going to block or filter OSPF packets. You can actually do that. You turn on an ACL that is specific to something, you can filter out your routing protocol. The interfaces also have to be on the same subnet and the same area. We'll see that that breaks things immediately. And then we have to have an OSPF process running, and that can also be for the interface as well. So if you decide to do the traditional global settings, right, we have to have that running, or we have to make sure that we have OSPF running on an interface. We have to have matching hello and dead timers. I think we talked about this last video. If your timers are mismatched, you won't be neighbors. And then you have to have unique router IDs. So we can't have the same router IDs out there. If you are doing authentication, if you're doing some kind of message authentication code or check, then that has to pass. And if it doesn't, then we're not going to accept you as a neighbor. Now there are some, I've got an asterisk here because these will prevent you from sharing router information, but won't necessarily break your neighbor relationship. And that is the same MTU, the max transmission unit, the same OSPF network type, and then we can't both use priority equals 0. We'll see what that means here in a little bit. Okay, so those are the things that we need for a neighbor relationship. There's a lot of them, right? Some of them are, sort of catastrophic losses of neighbor, and some of them are just like, well, this doesn't look good. I'm not sure if I want to be a neighbor with you. This was the topology that we're working with. And so in the demo this week, I'm going to break some things. So we've got, if we look at router 0 in this topology, right, this one right here in our topology, it actually has 3 OSPF neighbors. So all of the networks were broadcast. That's area 0 in the middle, and they're all on the same subnet. So everything was good for this. So we have 3 neighbors, and we're going to see if we can break those neighbor relationships using 3 different configuration errors. And of course, in a broadcast network, we're also going to elect a designated router, and in this case, a backup designated router. And that would break if we screw up the configuration settings bad enough, we won't have those either. So in the book, they talk about a couple of configuration mistakes. These are things that would cause a loss of your neighbor relationship. And what ends up happening is if you're watching the configuration, right, you'll see these changes immediately. But if we're going to diagnose this, right, something happens and then somebody tells you something's wrong and then you go in and start looking, an easy check is the show IP OSPF neighbor. So one of the examples that we're going to do is if we switch one of the routers to the wrong area, right? Right now we're all in area 0. If we change that, then that'll break our neighbor relationship. One router can be given the same router ID as another, and then if we have hello timers and dead timers that are mismatched. Now we did that one last week, so maybe we'll do something different this week. But we'll at least we'll break this a couple of ways. Now when we're troubleshooting, if we had the previous output or the previous configuration, even previous routing tables, we can take a look at those and compare them to what we have now, and maybe figure out what happened to our next hops, figure out what happened to our neighbors. But what we're doing is we're trying to ferret out where the configuration error happened. Now, the nice thing is that if we're logging things, right, we can log to the console. We can also log to a server, right, like a syslog server, and see what happened there. So why don't we go ahead and break some things right now. So here is our topology, and the only thing that I've added is this router right over here. We'll see why that's there later on. But if we take a look at our router right here, and we just take a look at what neighbors we have, we can see that we've got all of these neighbors. We're using these fun IDs for the routers, but we've got these forwarding IP addresses for the actual router IP addresses. So what if we take router 2 right here? Now, so everything is going to be done from the perspective of router 0. So we're going to lose all of these neighbors. So what if I say, we take a look, well, let's remind ourselves of our config first of all. Now in this one, we were doing things right on the interface level. And we know that our interface G001 is part of, right, the neighbor relationship. So what we're going to do is we're going to go to interface G0/0/1, whoops, like this, and we're going to say IP OSPF 1 area, and we'll just change it to 51. And we've got this mismatch area ID, right? You can see that it's quite grumpy about it. Now, what happened from the perspective of router 0 when this happened? We can see that our neighbor, right after a couple of complaints, all of a sudden we lost our neighbor. So that's a problem. So now if I take a look at my OSPF neighbors, right, if I knew that I had 3 neighbors before, all of a sudden I've lost one, which one did I lose? So it might be a configuration problem on this router, router 0, but we would also take a look at our router 1 here. Okay, so that's one way to lose a neighbor. Let's also see what happens. We'll go up here to router 3, actually router 2, but its ID is 3.3.3.3. And we'll do something else. Now, we already know about the timers. So what if I go to, we'll do a show run here. We'll take a look at this guy as well. And again, we're doing things on the interface. And we'll take a look at this interface right here that is going out to the 10.1.1 network. What if we change this to be on a different subnet, right? You just do, it's a very simple configuration error to make. But what if I did something like this, like that, and I say IP address. I'm just going to change it to the wrong network. So we'll say 10.11.11. We'll use the same address. And it doesn't even have to be as bad as all of that. I could say just 11.1.3, something like that. And again, if we take a look at router 0, so there's our message right there. So we saw that our other router was complaining that it was on the wrong network or that it was having a mismatch. But now if we take a look at our neighbors, now we're down to one neighbor. That's another way that we lost our neighbor just from a configuration mistake. And we'll do one more. So right now we can see that we've got a router ID of 4.4.4.4, and we got this router ID up here. Well, what happens if we make the mistake of saying, I like that router ID. I think what I'm going to do is use the same one all over the place. Now you can use the same process ID, but you can't use the same router ID. So this is where we set it right here. So now I'm just going to change it to the same value. Say router ID 1.1.1.1. Now, this will take just a second because we have to wait for this sort of to propagate. But remember that when the OSPF messaging goes back and forth, the router ID is included in there. And here we have a change from our last router that was our neighbor. So here we've lost our other neighbor. And we can see that if we take a look at our neighbors, we're in this very strange X-start state. And what that means is that they're trying to establish a neighbor relationship, but there's something wrong. And so that is the issue here. So this will never transition out of this state because they have the same router ID. Now I'm going to fix some of this because we want to be able to do an experiment later on. Now, as I said, all of these mistakes are easy mistakes to make, right? A mistake in an area, a mistake in an IP address, a mistake in a router ID. But they all cause catastrophic problems when you're trying to get your OSPF neighbor relationships established. Now, one of the other things that will cause problems, obviously, for your OSPF process or your OSPF configuration, your topology, is that if you shut down OSPF processes. Now this works, or this you can cause this to happen in either the traditional sort of global router OSPF process. You can just issue a shutdown command there, which clears the link state database and clears out all OSPF routes, brings down the neighbors, it does everything, which makes sense. The nice thing is that even if you did that, your OSPF config is still there, right? All that you did was shut it down. So you've got a full router OSPF build, and you just issue under the router OSPF process, you say shutdown. Then you didn't delete anything, and the router didn't kill off all of your config lines. So you might do this for testing. It might be a mistake. Now, if you go into the interface and you do the same thing, what happens then is anything that was specific to that OSPF interface. So anything you learned from that interface and anything you were doing on that interface, all of that ceases. So these are both potentially catastrophic to your OSPF topology, but one is global to the router and one is to the interface. Now, when we were going through all of the things that will cause a neighbor relationship to fail, I had an asterisk all the way down the bottom. That's because these things are problems, but they're not things that will stop you from being neighbors. They are things that will stop you from exchanging routing information. So that whole database exchange and the whole exchange of actual network destinations will not happen if you have these problems, right? So a mismatched MTU size. Now you can change that with the IPMTU, the MTU size command. The default is 1500 bytes. If you do a mismatched OSPF network type, remember last time we talked about being broadcast or point-to-point, and the primary difference between those is that while they both use discovery, only in the broadcast do we do the designated router and the backup designated router. The point-to-point routers know exactly who they're talking to, and so they don't need that. And in fact, the designated router process, that election would slow things down. So if you mismatch your network types, you can still be neighbors, but you might not share routes. And the reason for this is that when you have a different network type, your LSAs are structured just a little bit different. Now, neighbors that use the same priority of 0. Now, by default, routers use an OSPF priority of 1. And that's fine. They can all have the same priority. You'll do the election based on, right, the router ID. But 0 is a special case, which means I don't want to be a BDR and I don't want to be a DR. And so if you have a whole bunch of routers out there that have a priority of 0, that means nobody wants to be the DR, nobody wants to be the BDR, and so the neighbor relationship will fail. If everybody has a priority of 0, that means nobody wants to be the one that exchanges routing information. So you could be neighbors, right? But you're not going to exchange routes. So those three things will cause you to be neighbors, but not exchange routes. Now, this is a really, really important idea. What we're about to talk about here, the route selection. And this is whether or not you install a route, right? You already know a pathway to the destination, maybe, and you get some new information. Now you're going to ask yourself, should I put this in my routing table? Or if they're already installed in the routing table, which route do you take? So we're going to work ourselves through all of the main three fields, right? Prefix length, admin distance, and metric. Let me be clear here. At the top of this slide, right, the first couple of bullets are, what if you have an equal cost OSPF paths? What if routes are learned by different routing protocols? What if the route chosen there has more than one match in the routing table? So these are all problems. Okay, so let's take the first one. If there's more than one route to the destination and everything is the same, meaning that the prefix length is the same and you learn them via OSPF, right? So those two things are the same. Then the last thing to check is what's the metric? If the metric is 2 for one of the routes and 3 for the other one, well, 3 is a worse route. It's a bigger cost to the destination. And so the one that we would use or the one that we would install would be, in this example, 10.1.44.0/24, admin distance of 110 and a metric of 2. But what if you've got sort of a loop in your topology and you have two pathways to the same destination and the cost is the same, the metric is the same? Well, what OSPF does is it installs both of them. In fact, OSPF will allow you to have as many as 4 of the same pathway to the destination. So how does that work as far as routing packets? Well, when that happens, OSPF load balances across those links. But how does it load balance? Well, it might be easy to think, okay, well, I'll send one packet that way, one packet that way, one packet that way, one packet that way. But that's actually really hard to keep track of if I'm sending an IP packet for one destination IP this way, and then I send another packet to the same destination this way. So what OSPF does is it sends everything for one IP address that way and everything for another IP address that way. And usually when we load balance, there's a hash function that says, I'm going to divvy up the IP addresses and this collection will go that way and that collection will go the other way. And we see this all over the place when we're doing load balancing. And aggregation has the similar problem. And so while aggregation is at layer 2, We still have to divvy up the traffic based on, in this case, MAC address. Now let's take that next problem. Route selection based on administrative distance. What if I learned a pathway to a destination network via OSPF, and then I learned another pathway to the same destination subnet, but via some other routing protocol like RIP or EIGRP. Now, in the question example, it's EIGRP versus OSPF. What happens, or the problem is, that you can no longer use metric to compare them because each routing protocol uses a different metric. So RIP uses hop count, OSPF uses cost. So we can't compare routes in that way. So what we do instead is we have an evaluation of the information that is usually based on, sort of the quality of the routing protocol, kind of, sort of, right? It's a way to do some evaluation of the data. So every route type has an administrative distance associated with it. Lower numbers are better. The best possible route you could have is a directly connected route. And that should make sense, right? The router is directly connected to this subnet, and so this is the way that we're going to get to that subnet. The next best administrative distance is a static route. And the reason that it's just the best one out there except for directly connected is because, well, you said it. You decided that you wanted that traffic to go in that particular direction. And so that automatically overrides anything you would learn from a routing protocol. And then some other examples that the chapter has is EIGRP is 90, OSPF is 110, RIP is 120. So if you were comparing routes between EIGRP and OSPF, you would take the EIGRP routes every single time, no matter what the metric was. And that's actually one of the questions. The same is true if you were comparing OSPF learned routes and RIP learned routes. You would take OSPF over RIP every single time. And the bottom example that I put on the slides here is that the same destination network, right, 10.1.44.0/24. But we can see that even though the metric looks the same, that's not what we're going to look at. We don't really care because the administrative distance for the first one is lower than the second one. And so we would take that one every single time. Now let's do route selection based on the longest prefix match. It doesn't really matter what goes on in the administrative distance and the metric if one of your routes has a better prefix match. Now the goal is to have the longest prefix match in order to match the most specific route. In other words, it gets it much closer to the destination. Now the reason I've got a picture of a person and a bus and a plane, the analogy that I like to make for this is that if you have a really long prefix match, you're closer to the destination. So let's do the opposite. In the book example, we've got a destination network of 10.1.0.0/16. That's a big network. That's kind of like flying over an address and mailing a letter by throwing it out the door of the airplane. If we make the prefix length a little bit longer, that is, it's more specific, so 10.1.1.0/25, that might be like driving to the neighborhood and throwing it out the door. But if we make it very, very specific, like the last example, 10.1.1.1/32, that's like walking up to the door and sending it through the mail slot because it's very, very specific. Even a /30 would be much better than a /25 or a /16. Now, if I'm considering the IP address of 10.1.1.1, all three of those routes match that destination, right? That address is in those three address spaces. But one of them is a really large address space, and one of them is very, very specific. So we want the more specific match. We want the smaller address space, the longer prefix match. So when you are comparing routes, if one of them has got a longer prefix, that's the one that you take. If the prefixes are the same, then you go by admin distance. If the admin distance is the same as well, then you go by metric. So let me show you an example of what I mean by that. So if we take a look at the routing table for router 0, remember that I fixed the mistakes that we had earlier. We can see that we've got the 33 net available via 1.1.1. or 10.1.1.3, which is right here. And so traffic that would go to a destination host over here. So this router's IP address right here. Forgot we're doing the book. Okay. So if I ping from our router here and I do the simulation and I say ping 10.1.33.3, well, which way does it go? There we go. So we know which way that goes. Our goal now is to mess with that because I want to show you what happens when we start looking at things that will beat the OSPF route. So the first thing that I'm going to do is I'm going to configure our router here on this side. And all that I'm going to do is give it an IP address. That's all we really need. It's just a demonstration of which direction traffic is going to go. So I'm going to say int g0/0/1, and I am going to give it an IP address. Now this is the 10.1.11 network, so we'll say 254, like that. And just to verify connectivity, I'm going to say ping 10.1.11.1, I think is this IP address. There we go. So that is this IP address right here. Right? Maybe what we'll do is we'll zoom in just on this right here. So this traffic then is going between these two routers. And all that I'm doing is we're just showing that these two can talk to each other. Right? Okay. Well, what would I do to subvert my OSPF route? Well, an easy way to do that would be to put in a static route. So I'm going to say config T, and I'm going to say IP route, the same network, 33.0, right? But this time I'm going to say we get there via 11.254. So now if I see my routing table, so what we've added is this right here, this static route that's specific to the 33 net. Well, now which way does traffic go if I want to go to this network over here? Before it was going this way, right? But now, if I ping the same destination, which way does it go? It goes the opposite way. Why? Because in my routing table, take a look at my administrative distance. So let's review what's in the routing table, right? This line right here says that I'm chopping up the 10 net, right? The 10 net is a /8 class full space, but we've got all of these networks downstream. Our first column here is the matching criteria, and, well, I should say our first column right here tells me how I learned this. And here we've got our directly connected best possible route. Static routes are the next best, and we can see that my administrative distance here is 1. So that's going to beat anything except a directly connected route. And then we've got the forwarding IP addresses, how we get there. So these are just things to become familiar with as you're looking at your routing table. Now, what would be a way then for me to get the route back? Keep the static route there, but if I was going to use the OSPF route again, but having the same network in there? And the answer would be in the prefix length. The reason I took the static route over the OSPF route, right? We see the OSPF route is actually gone, is because the administrative distance was actually better. So the router said, well, which one do I add to my routing table? But let's modify this a little bit. I'm going to get rid of that particular routing statement. And instead, I'm going to say, let's route to that destination, but I'm going to make it a /16 now, like that. Like that there. Okay? So now what happens, if I look at my routing table, I can see I've got this static route right here. Now, if I ping 10.1.33.3, this routing table entry matches. But there's a better one right here because it's a /24. So where previously the static route won because of administrative distance, now the OSPF route is going to win because of the prefix length, even though a static route would normally be better. So again, we'll take a look at our simulation, and I will ping. And we can see that once again, it heads off across the middle network. And the whole point there is that we just showed that the router will pay attention to routes based on those three values. And it takes them in this order. The longest prefix length is better, followed by the administrative distance, followed by the metric. So our reminders, this is really, really important when you're manipulating the router configs and your router routing tables. That order of route selection is going to come back over and over and over again. And the prefix length becomes very, very important because it's a subnetting problem, or maybe even a supernetting or an aggregation problem. So you can't forget to practice your subnetting math. But no matter what, remember that the order of route selection will be prefix length first and foremost. If the prefix lengths are the same, then you go by administrative distance. If the prefix length and the administrative distance are the same, then you go by the metric. So don't forget to practice your subnetting math. All right, did you know this already? An engineer connects routers R11 and R12 to the same Ethernet LAN and configures them both to use OSPF2. Which answers describe a combination of settings that would prevent the two routers from becoming OSPF neighbors? So remember, these are things that we just did that would break the neighbor relationship. If you have an error or a timer mismatch, instantaneously your neighbor relationship is going to have problems, as we saw this video and the previous one. All right, question number 2. An engineer connects routers R13 and R14 to the same Ethernet LAN and configures them to use OSPF. No surprise. Which answers describe a combination of settings that would prevent the two routers from becoming OSPF neighbors? Now, this was, trying to get after the same topic. Routers using the same router ID will have problems, right? That was the one that they kept trying to be neighbors, but they couldn't because they had the same router ID. Question number 3. Router R15 has been a working part of a network that uses OSPF-v2. An engineer then issues the shutdown command in an OSPF configuration mode on R15. Which of the following occurs? Well, the answer to that one was D. The config is kept, but all OSPF activities cease. So everything is gone that you learned via OSPF, but the config lines are still there. So if you did a no shut, it'd be right back in business. Question number 4. Using OSPF, router 1 learns 3 routes to the subnet 10.1.1.0/24. The first calculates a route through router 2 with a metric of 15,000, and then a route through router 3 with a metric of 15,001, and then a route through router 4 with a metric of 15,000 again. Which routes does the router place into its routing table, assuming that all default configuration settings for any features that would impact the answer? Well, we now know the answer. We're going to do an equal cost multipath thing. So the metric is the same. to that destination from 2 different routes. So it would install both of the routes with the lower metric of 15,000. Question number 5, router 2 runs both EIGRP and OSPF. So it's doing EIGRP out one way and OSPF out the other. It learns 2 OSPF routes to subnet 172.16.1.0/24, one with a metric of 1,000 and one with a metric of 2,000. It learns 2 EIGRP routes with metrics of 1,000,000 and 2,000,000, huge metrics. If using the default settings for any settings that might impact the answer, which routes will the router place in the routing table? And the answer here, even though the EIGRP routes have a huge metric, EIGRP has a lower admin distance when compared to OSPF. And so the EIGRP route with a metric of 1,000,000 would be installed. Question number 6, router R3 receives a packet with a destination IP address of 172.20.89.100. How many of the address ranges defined in the routes per the show IP route command match the packet's destination address? All right, well, we know right away that the default route is going to match, so that's 1. Now the destination is 89.100. If we look all the way at the bottom, 172.20/16, that covers that, so that's 2. 172.20.80.0/20, well, that's actually 80.0 to 95.255, so that covers it. That's 3. And then the next route up, the 172.20.88.0/23, that's actually 88.0 to 89.255, so that one covers it as well. The next one up does not, so the answer was there are 4 routes that actually match that destination, all with different masks. Now the question would be, which one would you take? It would be the one with the longest prefix length. But that's why looking at routing tables is sometimes a subnetting problem. Question number 7, router 3 receives a packet with a destination address of 172.20.90.1. Which next hop IP address does router 3 use when forwarding the packet? And the answer was C, 172.20.13.3. Now that's this address down here. The bottom entry matches, but it's got a very short prefix length. So this one here has a better prefix length, the longer one gets it closer, it's more specific. This one here does not match because this is 88 and the 89 subnets, so it doesn't match. This one here is too specific, and so it's not this IP address. So that's why it is the answer right here, 172.20.13.3. Whew, so that's been OSPF. That's a lot of OSPF. Our Chapter 25 look ahead, it's time for IPv6. So this will be fun. We'll do IPv6 fundamentals. So we'll configure some IPv6 addresses and prefixes. We'll see how those look. And we'll work with the IPv6 address types. You're going to love this. It's kind of crazy to look at, but there's a lot more to IPv6 than just these crazy long IP addresses. So that'll be fun to look at. So this has been OSPF neighbors and route selection. So what do we need to be OSPF neighbors, right? It's not a given just because you're going to send out an OSPF hello. There have to be a whole bunch of things that match. So we saw that. And what would break that? And then we would use our show IP OSPF commands and then the show IP route commands, show run commands to do that troubleshooting to figure out what mistake we had made. Remember, when you are working with route selection, it's the big 3. Prefix length is number 1, the big dog. So if the prefix length is long, then that's the one that we want because it's most specific when compared to one that's, say, class full. If the prefix lengths for the 2 paths or 3 paths are the same, then we're going to pick the admin distance. Remember that the best possible admin distance is a directly connected, followed by static, followed by whatever routing protocols you're using. If the prefix length and the admin distance are the same, then we're going to go by metric. All right, so that's OSPF, and route selection. I hope you enjoyed this OSPF series and these chapters in CCNA, but like and subscribe if you are ready to go for IPv6. I know I am. And no matter how you made your route selections, may those packets always reach their destinations. And remember that we're on the road to CCNA. We're tackling IPv6. We're done with OSPF. You can do this. And I'll see you in the next one.